All right, so I'm in a work problem 28 from your text on page 156. It says 1,000-kilogram car traveling at a speed of 40 meters per second skids to a halt on wet concrete where mu sub k, or the coefficient of kinetic friction, is 0.6. How long are the skid marks? So for this problem, I'm going to start out by, first step is going to be draw the free body diagram. And I also noticed that there was some motion information in there. So it gave me an initial and final velocity. So I'm going to record a list of variables that I have information about. And then the next step that I am going to do is to, once I have my free body diagram and my list of variables, I'm going to think about how I could find, how could I get to the information they're asking me for. So I'm going to need to find delta x. They're saying the distance, the displacement of the, displacement of the car during the braking process, right? From when it was at 40 meters per second to when it was at 0. So I'm going to be thinking about what equation might I be able to use to find delta x based on those variables. And I know there's going to be another step in here where I'm going to have to probably find some more information before I can use this equation. So I'm going to kind of leave this list here, do my free body diagram, and then work back through what my next steps will be based on my diagram. So I have this car. I know that the car has a mass of 1,000 kilograms. And so right away, I'm going to just go ahead and calculate the force due to gravity is mass times acceleration. Mass is going to be 1,000 kilograms times my acceleration due to gravity on Earth is going to be 9.8 meters per second squared. Again, you can use 10 if you prefer. And so we get 9,800 newtons. Now, is my car accelerating upward into the sky? Is it accelerating down, making a hole in the ground? Nope. It is in balance in the vertical direction, so my forces have to be balanced. So I know that my normal force is going to equal my force due to gravity. And so that's also going to be 9,800 newtons. That's important because I know that whenever I'm braking a car, what force is it that's stopping the car? It's actually the friction of the tires on the surface. So I know I'm going to deal with frictional force. I know I'm going to need to know my normal force for that. And then, like I said, the only force on the car, it started going 40 meters a second. It's getting down to 0. It's accelerating. So one thing I might want to label on my diagram is just my velocity. My direction of motion is actually this way. I'm not putting that on here because it's not a force, right? If my car is going 40 meters a second, inertia would keep it going at 40 meters a second unless a force acts on it that causes it to accelerate. And it is accelerating in the opposite direction of motion. That's what slowing down is. Acceleration, opposite the direction of motion. And what force is causing that acceleration? Well, it's my kinetic friction force, right, from the braking. All right, so the next step is for me to think about what do I need? What equations are available to me for finding delta x? So there are two on my equation sheet. One that kind of, I didn't do my list of variables. I'm going to do my list of variables because that helped me decide what equation I want. So what variables do I have information on in terms of motion? I know that my initial velocity is 40 meters per second. I know my final velocity is 0 meters per second because my car is coming to a stop. And I know I'm trying to find delta x. So because I have initial and final velocity, when I look at my equation sheet, I see that I have an equation that says final velocity equals initial velocity plus 2 times the acceleration in the x direction times delta x. So I'm going to be able to find delta x here using these numbers that I'm given if I can find acceleration. So my missing step here is I'm going to need to find acceleration. And generally, when we go from the free body diagram to acceleration, we're going to be thinking about F equals m times a. So Newton's second law, I can calculate acceleration using this. But my acceleration is in the horizontal direction. So what force is in the horizontal direction? It's my kinetic friction force. And I can find that because I know that, so before I can find A, I'm gonna have to find F. So I'm gonna find F. F for kinetic friction using that equation, F for kinetic, or force of kinetic friction is equal to mu times the normal force. So I'm going to go ahead and work through this process. So I have my free body diagram, my list of variables. I kind of worked backwards here. I figured out what equation I needed, what variables I need to find, and then I came up with my process. So now I'm going to go ahead and do my process. My force of kinetic friction is going to be equal to mu, which mu is given in the problem. I should have put that here. Mu for this problem is 0.6. And you notice mu doesn't have a unit. So 0.6 times my normal force, and my normal force is 9,800 newtons. So this is mu times my normal force. And so when I do this, I find that my force of kinetic friction is 5,880 newtons. And then the next step that I'm going to do is to find acceleration. So now that I have F, I did step one, I did this. Now I'm going to find A using F equals m times A. So force equals mass times acceleration. I know the mass of the car was 1,000 kilograms. I know the force, I just found it here, and so now I can find A. So algebraically, to solve this equation for A, I'm going to solve it for A. I would need to divide both sides by m because m and a are connected by multiplication. I have to do the opposite math to get rid of m from the side. And so I find that A equals F divided by m. F I'm going to get from right here. My force due to kinetic friction is 5,880 newtons. And my mass from the problem is 1,000 kilograms. And when I do the math, I find that my acceleration is 5.88 meters per second squared. So one thing that's challenging is that often when we're working with the free body diagram, when we're working with just solving F equals ma, we don't necessarily assign negative values to things. We tend to do it when we're like getting ready to like find our net force, then we might put a negative sign on something, but a lot of times we might not do that. We might leave it positive and then we get a little bit confused. So I want us to pause for a second and think about force of kinetic friction is moving this way. So really, when I write the number, I should be putting a negative sign on it. When I do this math, my acceleration vector is opposite my velocity. Whenever I'm braking, I'm slowing down, it means my acceleration vector is going the opposite direction from my velocity vector. So my acceleration is in the negative direction. So I have a negative 5.88 meters per second squared. And that's going to be important when I'm solving for delta x from this equation. So now I'm going to come here and I'm going to solve this equation for delta x. So first of all, I have a VI over here that I want to move away. I'm trying to get delta x by itself. So I'm going to say VF squared minus VI squared equals 2A delta x. So I subtracted VI squared from both sides. This goes away, ends up on the other side. Now I still need to get delta x alone. 2 times A times delta x. What math is holding them together is multiplication. So I need to divide 2A on both sides. And when I divide by 2A, this cancels out. So I end up with delta x equals final velocity squared minus initial velocity squared over 2A. I know my final is 0. I know my initial is 40. You'll notice the top here is ending up negative because I have 0 squared minus 40 squared. And so it's important that I have this negative acceleration here because now when I put that in there, I have negative on top and on the bottom. They're going to cancel out. I'm going to get a positive delta x because my car is moving to the right. So my displacement will be positive. All right, so when I did this math, I ended up with 136 meters as my final answer for delta x. Leave that for a second. And that's the end of that one.